Next topic is Caratherder theorem for differentiable function. Caratherder theorem for differentiable function. So let I be interval and C is the element of I. C belongs to I. Then the function f from I to R is differentiable at point x is equal to C if there exists a function g from I to R, is capital I to R, such that gx is continuous at x is equal to C. This new function gx is continuous at x is equal to C and satisfies the condition f of x minus f of c is equal to gx in bracket x minus c. So this is the Caratherder's theorem for differentiable function. That is, so this is the statement of this theorem. The proof of this theorem is not included in our syllabus, so just remember this statement of the Caratherder's theorem. So next theorem, there are three theorems with proof. What are that? Rolle's theorem, Lagrange's mean value theorem, and Cauchy's mean value theorem. LMVT, Lagrange's mean value theorem, and Cauchy's mean value theorem, CMVT, and LMVT, and Rolle's theorem. So out of this, the probability of one theorem is what? 100%. That is state and prove. And one example is also on this theorem. So as far as the exam concerned, these three theorems and their examples are important. So first theorem is Rolle's theorem. So what is the question? That question is state and prove the Rolle's theorem. That is, we learn the proof as well as the statement of the theorem. That is, let f be a function. Number one satisfies these three conditions. That is, number one, f is continuous on AB, closed interval AB, differentiable on open interval AB, and the third condition is f of A is equal to f of B. That is, the value at the first point and the value at the last point both are same. Then there exists at least one point C belongs to open interval AB such that f dash C is equal to 0. The derivative of at that point is equal to 0. So in between A and B, there exists at least one point C such that the derivative at that point is 0. But when this happens, if the function satisfies these three conditions, that is continuous on closed interval AB, differentiable on interval AB, and third condition is what? F of A is equal to f of B. Then there exists at least one point C belongs to open interval AB such that f dash C is equal to 0. So this is the statement of the theorem. So what we have to prove? This is up to this these three conditions are given. We have to show that there exists a point C belongs to open interval AB such that f dash C is equal to 0. So these given is what? F is continuous on closed interval AB, f is differentiable on open interval AB, and for f of A is equal to f of B. So these three conditions are given, and we have to show that then prove that there exists at least one point C belongs to open interval AB such that f dash C is equal to 0. Derivative at that point is 0. So the proof of this theorem, as f is continuous, so f is bounded and attains its bounds for some point in closed interval AB. So if the function is continuous, then function is bounded. So when we say the function is bounded, if the function has supremum and infimum or upper bound and lower bound, then we say, that is, if function is both bounded above and bounded below, like sequence, then we say the function is bounded. So when the function is bounded, if its set of images is bounded, and when any set is bounded, when the set is bounded, if it has a upper bound and lower bound. For example, we consider the set of natural numbers, some natural number that 1, 2, 3 up to 100, the set of the 100 element, that is 1 to 100. So this set is bounded set. Why? Because 100 and all numbers greater than 100 are its upper bounds. Okay. So, and 100 is its what? Least upper bound. Okay, that is supremum. And 1 and less than one number, all numbers less than 1 are what? Lower bound of the set 1 to 100. And so the set is bounded below. So, and one is its what greatest upper bound, that is the infimum. So infimum is what's greatest upper bound, greatest lower bound, and supremum means what? Least upper bound. Greatest lower bound, that is GLB means infimum. So one is what? Is the greatest lower bound. That is all the numbers 1 and less than 1 are upper bounds, not upper bound, lower bound, and out of these 1 is the greatest. So greatest lower bound means infimum is 1 and supremum is 100. So in the last semester, in the first semester, we already learned this thing, that infimum and supremum. So when the function is called bounded, if its set of images is bounded, suppose the set of images contains suppose 100 elements, then if this set is bounded, then we say that is if this set is bounded, it's upper if the for this set, if upper bound and lower bound both exist, then we say the set is bounded. So if the set is bounded, if the function is bounded, it has a supremum and infimum. So small m and capital M is infimum and supremum of the function m. Then clearly small m is less than or equal to capital M, because infimum is always less than or equal to capital M. So what are m and small m and capital M? Infimum and supremum of the function m means this small m and capital M are infimum and supremum of the set of images of under the function m. So note these things, that small m. So that is small m is image of some function, some element under this function m, and capital M is also the image of some element from the set AB. Okay, because this function f is function from closed interval AB to R, the function. Okay, so if case number 1, m is always less than, small m is always less than or equal to capital M. Case number 1, suppose small m is equal to capital M. Then what happens? Then the function f is constant function on closed interval AB. When we the supremum and infimum are same, if the set contains only one element, then supremum and infimum of that set are same. Supremum and infimum, if the set contains only one element, then the set has a infimum. For that set, supremum and infimum both are same. So small m is equal to capital M. Therefore, the set of images under the function f has only one element. That is image of. That is the image of every element is a fixed, is constant, some constant number under the function f. The image, that is the function is of this type, fx is equal to 5. Fx is equal to 5, constant function. Okay, so because the set of images for the set of images small m and capital M, that is supremum and infimum, are same, therefore f is a constant function. Otherwise this is not happen. That is, if the function fx is of the type x plus 2, for example fx is equal to x plus 2, then under this function image of 1 is 3, image of 2 is 4, image of 3 is 5. That is, the image of all elements are not same. So when the image of all images are same under the function, if the function is constant function, so small m and capital M are same. That's why that is supremum and infimum of the function are same, and therefore the function f is constant function on closed interval AB, and therefore its derivative F.C is 0 for all elements under for all C belongs to open interval AB. Therefore the function derivative of the function, constant function, is 0 everywhere, and therefore we have infinitely many points such that at that point the derivative of the function is 0. So this statement is now true that there exists at least one point. Here we have infinitely many points between A and B such that the derivative at that point is 0. That is F.C is 0 for all C belongs to open interval AB, because the derivative of constant function is 0 for every point. Okay. The next second case, suppose this small m is strictly less than capital M. Then what happen? M or capital M is different than f of A is equal to f of B. We are given f of A is equal to f of B. So what happen if both are is equal to f of A or f of B? Then what happen? M small m is equal to capital M. So this small m is strictly less than capital M, means m is not equal to capital M, and therefore m small m or capital M is differ than f of A is equal to f of B. Let suppose this capital M is not equal to f of A is equal to f of B, and then suppose there exists another point C belongs to open interval AB such that capital M is equal to f of C. So m and small m and capital M are images of some elements from the set AB. Okay, but this capital M is not equal to f of A or f of B. That is, capital M is not the image of small a or small b. Means there exists another element between A and B such that, suppose C, such that capital M is equal to f of C. That capital M is image of that C. Then therefore we have f of C is greater than or equal to f of x for all x belongs to open interval AB, because f of x is greater than or equal to f of x for all x belongs to open interval AB, because this capital M is supremum of the set of all images. That is, the f of C is what is greater than or equal to f of x for all x belongs to open interval AB. That is, this f of C, image of C under F, is large or equal to all the images under the function F. So f of C is greater than or equal to f of x for all x belongs to open interval AB. And therefore we have, because so M is capital, FC is supremum. Supremum is always large than all the remaining elements in that set. Okay, and therefore f of x minus f of C divided by x minus C is greater than or equal to C. So f of x is larger than f of C. So this quantity is what, either equal to 0 or is what, positive quantity, because f of x is this is negative quantity. Negative quantity. Fx is what? Fx is what? Is less than f of C. So if we subtract larger number from smaller number, we have negative answer. So this is negative, and negative divided by negative is what? Is positive number. So this is negative because fx is what? Less than f of C, and so f of x minus f of C is negative. And if x is less than C, then what happens? X minus C is negative because x is smaller than C. So if we subtract larger quantity from smaller quantity, then we have the answer negative. So this quantity is negative, and negative by negative is greater than 0. And when this is equal to 0, if f of C and f of x both are same, then f of x minus f of C is 0. In that case, we have equal to 0. So this f of x minus f of C divided by x minus C is greater than or equal to 0 if x is less than C. And if x is greater than C, the negative divided by positive is less than 0. So this f of x is less than f of C. So f of x minus f of C is negative. And if x is greater than C, then x minus C is positive. So negative divided by positive, answer is less than 0. So and equal to 0, when it is equal to 0, if f of C and f of x both are same, then f of x minus f of C is 0. In that case, we have equal to 0. Okay. As C is the element of open interval AB, and so by condition number 2, what is the condition number 2 given? The function is differentiable on open interval AB. That is, the function is differentiable for at every point lies between A and B. Okay, and so C is the point lies between A and B. C belongs to open interval AB, and so by condition 2 given in the theorem, F'(C) exists or F is differentiable at x is equal to C. And so F'(C) is exist means F'(C) is equal to F'(C) plus is equal to F'(C) minus. When we say the function is differentiable at x is equal to C, if right hand derivative is equal to left hand derivative is equal to the derivative of the function. Okay. So as the function f is differentiable at x is equal to C, F'(C) exists, and therefore F'(C) is equal to F'(C) plus is equal to F'(C) minus. So if the right hand derivative and left hand derivative are same, then we say the function is differentiable at that point, and its value is equal to F'(C). It is denoted by F'(C). What is F'(C)? Is either F'(C) plus or F'(C) minus, because these both are same. So as the function C point belongs to open interval interval AB, and therefore f dash c exists or f is differentiable at x is equal to c, and therefore we have this, that f dash c plus is equal to f dash c minus is equal to f dash c. And therefore f dash c is equal to f dash c plus is equal to, what is the value of f dash c plus? Its limit extends to c plus f of x minus f of c divided by x minus c, by using the definition of differentiability. First, this is the definition of differentiable function. So when we say the function is differentiable, this f dash c is what? Limit extends to c f of x minus f of c divided by x minus c. And what is f dash c plus? Its limit extends to c plus fx minus f of x divided by x minus, and this is the f dash c minus, okay, left hand derivative. So f dash c is equal to f dash c plus, here we have f dash c is equal to f dash c plus, and what is the value of f dash c plus? Limit extends to c plus f of x minus f of c divided by x minus c, and this quantity is less than or equal to 0. This limit is less than or equal to 0 because f of x minus f of c divided by x minus c, x tends to c plus means x is greater than c. X tends to c plus means x is greater than c, and if x is greater than c, then this quantity is negative. F of x minus f of c divided by this quantity is what? Negative, and therefore its limit is what? Also negative, less than or equal to 0, because this quantity is what? Less than or equal to, because c tends to c plus, x tends to c plus means x is greater than c. Okay, and what is f dash c? Again, f dash c is what? F dash c minus, and what is f dash c minus? Left hand derivative, limit extends to c minus fx minus f of x, f of c divided by x minus c, and as x tends to c minus, that is x is less than c, and if x is less than c, then f of x minus f of c divided by x minus c is greater than or equal to 0, and therefore limit of this quantity is what? Greater than or equal to 0, and therefore f of c is what? Less than or equal to 0, and f of c is greater than or equal to 0 implies f of c is equal to 0, because we have f dash c is less than or equal to 0, f dash c is greater than or equal to 0. This implies f dash c is equal to 0, because the same quantity is not less than 0 and greater than 0, means it is equal to 0. And we have the theorem, that is hence the theorem, that is we have the point between a and b belongs to open interval AB such that f dash c is equal to 0. So this is about the Rolle's theorem, the proof of Rolle's theorem. Then geometrical meaning of Rolle's theorem. So draw this figure. This is the curve y is equal to fx, and f of a and f of b both are same. So starting point and ending point, value at starting point and ending point. Suppose this is point A, this is point B, and show the f of A and f of B are equal, means show A and B, these 2 points at the same level. So f of A is equal to f of B. And this is the curve of that function y is equal to fx. Then geometrically, Rolle's theorem states that if the function f is continuous on closed interval AB and variable on open interval AB, and the third condition f of A is equal to f of B, that is if the function satisfies 3 conditions of Rolle's theorem, then there exists at least one point C belongs to open interval AB such that f dash C is equal to 0. Means what? F dash C is equal to 0 means what? F dash C means the slope of the tangent at point C, and the slope of the tangent at point C is 0 means the tangent is parallel to x-axis. When the slope of the line is 0, if the line is parallel to x-axis, then its slope is 0. So f dash c is equal to, what is the meaning of f dash c? F dash c means the slope of the function at point C. So slope of the function tangent f dash c means what? Is the tangent at the point C, and it is equal to 0 means its slope is 0. The slope of the tangent f dash c means slope of the tangent at the point C is equal to 0 means it is a parallel to x-axis. So here we have 2 points in the figure. We have the 2 points C1 and C2. At that point also this C2, C3. So at these 3 points, draw this tangent to the at that point, at the point C1 and at the point C2, draw the tangent such that these tangents are parallel to x-axis, because that slope are equal to 0. So geometrically, Rolle's theorem states that if the function f is continuous on closed interval AB, and second is variable on open interval AB. Then and third condition is f of A is equal to f of B. Then there exists at least one point C belongs to open interval AB such that the tangent at that point is parallel to x-axis. Is parallel to x-axis. F dash C is equal to 0 means the slope of the tangent is equal to 0. At that point C, the slope of the tangent is 0, and when the slope of the tangent is 0 means the tangent is parallel to x-axis, because when the slope of line is 0, if the line is parallel to x-axis. So this is the geometrical meaning. So question on this theorem is what? State and prove Rolle's theorem and give its geometrical meaning. So this is the geometrical meaning or geometrical interpretation of Rolle's theorem. Then next theorem is what? Lagrange's mean value theorem. So the question is what? State and prove Lagrange's mean value theorem. So this is the statement and the proof, and the next one is Cauchy's mean value theorem. So we'll see these two theorems in the next lecture.